Good morning. Today we will study about the ionic solids. Ionic solids contain an ionic bond which is formed between atoms by the complete transfer of one or more valence electrons of one atom to the other atom. Therefore, in this type of bonding, one atom complete its octet and acquire noble gas configuration by losing the electrons and other by gaining the electrons. The atom which loses the electrons acquire a positive charge and the other which gains the electron acquire a negative charge. These two oppositely charged species come closer due to electrostatic forces of attraction and form an ionic bond. The electrostatic forces of attraction which holds the oppositely charged ion together is known as ionic bond or electrovalent bond. The compound containing ionic or electrovalent bonds are called ionic compounds. How ionic bonds are formed? That is formation of ionic bond. An ionic bond is formed when one or more electrons are completely transferred from one atom to another atom so that both the atoms acquire stable noble gas configuration. Suppose we can take the example of sodium chloride. In sodium chloride, how the formation of ionic bond takes place. Sodium atom has only one electron in the valence shell, and by losing this electron it can acquire stable electronic configurations of neon. On the other hand, chlorine atom has 7 electrons in its valence shell and needs only one electron to complete its octet. Thus both the atoms can complete octet if sodium atom gives one electron to chlorine atom. This tendency is responsible for bonding between sodium and chlorine atoms. Therefore, sodium gives electrons and become positively charged species, while chlorine takes up the electrons and become negatively charged ion. These two ions are then held together by electrostatic forces of attraction, which constitute an ionic bond. When an atom combined by electron transfer, the number of electrons gained or lost must be equal so that the resulting compound on the whole is electrically neutral. The number of electrons gained or lost by an atom in the formation of ionic bond is equal to its electrovalency. An atom that readily loses electrons are said to be electropositive, while those which readily gains electrons are called electronegative. General characteristics of ionic solids. The ionic solids have the following characteristics. Number one, they are crystalline in nature. Ionic compounds are crystalline in nature. X-ray study of these compounds have shown that they do not exist in the molecular form but consist of ions of oppositely charges arranged in some definite geometrical pattern, and each ion in the crystal is surrounded by a definite number of oppositely charged ions. The geometrical arrangement of ion is different for different ionic substances. Number 2, high melting and boiling points. In general, ionic compounds have high melting and boiling points and high heat of fusion and vaporization. This is due to strong electrostatic forces of attraction between the oppositely charged ions. Number 3, hardness. Ionic compounds are hard and rigid, and hardness is due to the strong electrostatic forces of attraction between oppositely charged ions. Number 4, brittleness. Ionic compounds are usually brittle, that is, they can be easily broken into pieces on applying stress. Number 5, solubility of ionic compounds. Ionic solids are soluble in water and other polar solvents having dielectric constants. Since water has a high dielectric constant, it decreases the electrostatic forces of attraction between the ions. As a result, the ions get separated from one another to give a solution. And ions in the solution acquire greater freedom of the motion. Number 6, conduction of electricity. Ionic solids consist of ions. They do not conduct electricity in solid state. Why? Because in that the anions and cations on account of the strong electrostatic forces are strongly held at particular position in the crystal lattice and they are not free to move. Means there is no current follows. However, as the temperature is raised, there is increase in the kinetic energy of the ions, and when the substances are heated to high temperature so that they melt, the kinetic energy of the ions increase to such a large extent that they overcome the attractive forces and become mobile and are thus able to conduct electricity in the molten state. Number 7, ionic reactions. Ionic compounds split up into oppositely charged ions when dissolved in water. The chemical reactions of ionic compounds are characteristics of the constituent ions are known as ionic reactions. Number 8, non-directional. The ionic bond is non-directional. That is, in ionic compounds, each ion is surrounded by the oppositely charged ion held together by the electrostatic forces, and these forces are uniformly distributed all around the ion. That is, electrical field is non-directional. Therefore, ionic bond is non-directional. Then, close packing of the ions. The closely packed arrangement is that in which maximum available space is occupied, and closer the packing, the greater is the stability of the crystal. Now, to understand the packing of the constituent particles of a crystal, let us consider the packing of hard spheres of equal size in 3 dimensions. If the number of the spheres of equal size are put in a container and shaken, it is observed that they pack themselves in 2 common ways, shown in the figure. In arrangement 1, the spheres are packed in such a way that the rows have horizontal as well as vertical alignment. And in this arrangement, the spheres are found to form squares. In arrangement 2, the spheres are packed in such a way that spheres in every second row are placed in the depressions between the spheres of the first row. In the third row, the spheres have vertical alignment with the spheres in the first row. Now, if we compare the 2 arrangement of the spheres, that in arrangement 1, the spheres are less closely packed than the arrangement 2, and it has been calculated that in the first arrangement only 52.4% of the space is occupied by the spheres, and the remaining 47.6% of the space is empty and is called void. And in the second arrangement, 60.4% of the space is filled and 39.6% of the space is empty. Thus, the arrangement 2 is more economical and it is a close packing of the spheres. Now, in the closed packed arrangement, that is arrangement second, the center of the nearest pairs are at the corners of the equilateral triangle as shown in Fig B. Each pair is in contact with 6 other similar pairs, and the number of the nearest neighbors with which a given pair is in contact is called its coordination number. Thus, the coordination number of each pair in the closed packed arrangement is 6. Now we can say that arrangement second represent close packing of these pairs in a layer. We can build other layer above the first layer to extend the packing in the 3 dimensions. Now label these pairs in the first layer as A, and it is clear that there are 2 types of the voids in the second layer, and these are marked as A and B, and all the hollows are equivalent, but the pairs of the second layer may be placed either on the hollows which are marked as A or on the other set of the hollows marked as B. And it is noted that it is not possible to place pairs on both type of the hollows. Thus, while building the second layer, only half the hollows are occupied and half of the hollows remain unoccupied. Now, if we place the pairs on hollows marked B to make the second layer, which may be labeled as B layer, the second layer is represented by the dotted line. When we come to packing of the third layer, there are again 2 types of the hollows available. One type of the hollows marked A are the unoccupied hollows of the first layer, and the other type of the hollows are hollows in the second layer which are marked as C. Thus, there are 2 alternatives to build the third layer. If the pairs of the third layer may be placed on the hollows of the second layer, that is on C. Each pair of the third layer lies directly above those in the first layer as shown in the figure. This arrangement, if continued indefinitely in the same sequence, it represents AB type of the arrangement, and this type of the packing is known as HCP type of the packing. This is the HCP type of the packing. In this figure, the pairs of the third layer are not shown because they are identical to A layer, and for simplicity it may be drawn as shown in the figure. Next, A in HCP type of the arrangement. The second layer to arrange pair in the third layer is to place them over the hollows marked A, and this gives rise to a new layer labeled as C, and this will give a different type of this closed packed arrangement. And however, it is shown that pairs in the fourth layer will correspond with those in the first layer, and this type of the arrangement may be represented as ABC type of the arrangement, and this is known as cubic closed arrangement. This is known as cubic closed packed arrangement and abbreviated as CCP. And it is clear that there is a sphere at the center of each face of the cube. Therefore, this arrangement is also known as face-centered cubic arrangement, and it is abbreviated as FCP. It may be noted that both type of the packing are equally economical, though these have different forms, and in both these arrangements 70% of the available volume is occupied by the spheres. In addition to the above 2 closed packed arrangement, there is another arrangement of the packing spheres which is known as body centered arrangement. And in body centered cubic packing of the spheres, it is abbreviated as BCC, and in this arrangement the spheres in the third layer of the close packing are slightly opened up, and this is shown in the figure. And the spheres in the second layer, which are shown by the dotted spheres, they are placed at the top of the hollows in the first layer. And it is clear from the figure that these spheres in the second layer is in contact with four spheres of the first layer. And in the third layer, the spheres are placed exactly above the first layer. Therefore, in this arrangement, each sphere is in contact with 8 spheres, 4 in the layer below and 4 in the layer above it. And this arrangement can also be described as cubic arrangement, in which there are 8 spheres at the corners of a cube and 1 sphere is in the center or body of the cube. And in PCC arrangement, only 68% of the volume is occupied, and therefore it is less economical as compared to HCP or CCP arrangement. Now, what are the interstitial sites in close packed arrangement? We have seen that even in the close packing of the spheres, some hollows are left vacant, and these hollows or voids, and these are known as interstitial sites. These sites are named depending on the geometry in the terms of the positions of the atoms surrounding the holes. For example, in close packed arrangement of the spheres, the center of 3 spheres lies at the vertex of an equilateral triangle. The empty space between these spheres is called triangular site. There are 2 types of the voids or interstitial sites in the crystals, and these are tetrahedral sites and octahedral sites. In tetrahedral sites, this type of the site is formed when a sphere is in the second layer is placed above the 3 spheres touching one another in the first layer. And the center of the 4 spheres are disposed towards the corners of a regular tetrahedron. And the shape of the hole is not tetrahedral, but the arrangement around the hole is tetrahedral. That's why the hole is tetrahedral site or tetrahedral hole, because the shape of the hole is not tetrahedral, but the arrangement around the hole is tetrahedral. Arrangement of spheres around the hole is tetrahedral. And in octahedral sites, octahedral site is formed when this type of this site is formed at the center of the 6 spheres, and the center of which forms a regular octahedra. It is clear that octahedral site is formed by 2 sets of equilateral triangle which point in opposite directions. Now, what are the ionic structures? We have seen that in the formation of the crystals, the constituent particles, they get closely packed together. The closely packed arrangement is that in which maximum space is occupied, and the closer the packing, greater is the stability of the crystal. And the crystalline substances have definite orderly arrangement of their constituent particles in 3 dimensions. The regular arrangement of the constituent particles of a crystalline solid in 3 dimensional space is called space lattice. And the smallest repeating unit in space lattice, which when repeated over and over produce the complete lattice, is called the unit cell. The smallest repeating pattern or unit cell represents the shape of the entire crystal. And it may be remembered that while drawing the structure of ionic solids, we do not draw the complete crystal lattice but a unit cell. And in the simple ionic compounds, generally two types of the arrangements are possible. These are the CCP, that is cubic close packed, or HCP or hexagonal close packed arrangement. And the larger ions, that is anions, they adapt this arrangement. The CCP arrangement, also known as FCC arrangement, can be obtained by placing atoms at the corners of the cube and at the center of each face. This arrangement is also called ABC type of the arrangement, and there are 4 atoms per unit cell in this arrangement. The SCP arrangement is drawn by placing atoms at all the corners of the hexagonal faces and at their center. One layer is made in between these two identical layers. If we join opposite corner of a face, we get 6 triangles. The second layer is formed by placing the atoms above alternate triangles, and this arrangement is also called APAB type of the arrangement. The cation occupy the interstitial sides of this arrangement, because there are 2 types of the sides which are commonly occupied. That is octahedral sides and the tetrahedral sides, and there are 2 tetrahedral sides for each atom and 1 octahedral sides for each atom. Now, what are the locations of the tetrahedral sides and the octahedral sides? The octahedral sides in CCP arrangement are between the 2 anions. Obviously, there are at the center of every edge and in the body center. Only the octahedral sides of top face are shown by dark spheres. The hollow spheres represent anions. If we carefully see the CCP arrangement, we observe that it has 8 small cubes. Each cube has 4 anions at the alternate corners, and center of the small cube becomes the tetrahedral site. And there are 8 small cubes, and therefore there are 8 tetrahedral sides. Only 1 tetrahedral site is shown. In SCP arrangement, the octahedral and tetrahedral sides are shown in the figure, and we have learned earlier that the second layer in SCP arrangement is made by placing atoms on the alternate triangles in the face. For example, B layer is formed by placing atoms above the triangles marked crosses. The octahedral sides correspond to the other triangles not marked by the crosses in the figure. The tetrahedral sides are shown above and below each atom. For simplicity, only the tetrahedral sides above the bottom layer are shown. Tetrahedral sides above the bottom layer is shown. Let us discuss some important structures of 2 types, AB and AB2. In the structure AB type, the 2 types of the ions A plus and B minus have same coordination number, that is number of nearest neighbors. However, in the compounds of AB2 or A2B type of the 2 kinds of the ions A plus and B minus have different coordination numbers, which are in the ratio of 2:1 or 1:2. Though the close packed arrangement may slightly expand in order to accommodate the opposite ions, as a result the structure may be slightly open up structure, but the close packed structure is often a good starting point for the discussion of these structures. Okay, thank you. Have a nice day.